Good afternoon. I know I'm the last presenter before lunch, so I'll try to keep it a little bit on the light side. So Adam Wallen, I'm representing VEIR here today. And what VEIR is doing is looking and trying to solve some of the problems that we have as a civilization to get to decarbonization goals set for 2030 and 2050. So we're developing a next generation transmission product. And the trends that we look at and the data that we talk to about the problem to solve is that to meet the decarbonization goals out to 2050, conservatively, we need to increase the capacity of the grid, meaning high voltage transmission, by at least 3x, maybe 5x. Existing conductors, metal conductors, have a limitation on how much energy, power you can put through them literally before they melt. So the trends that we look at are really around the penetration of renewables. That train has left the station. To meet decarbonization goals, we need to take thermal generation offline and replace that with renewables. Renewables, high quality utility scale renewables, are remotely located, and load is where we need the power. So with solutions that many people talk about, utility scale long duration storage, that can be co-located with the renewable generation or co-located with the load, but you still need to get that power that's produced to where it's required. And that's where VEIR is really looking to innovate. Just a benchmark to give you an idea of the size of the market itself, in North America alone, this is just the US market, about $15 billion a year is deployed in CapEx only for distribution projects in the US. As you look at these electrification cases, high and medium, out to 2050, again, that's where we talk about that 3 to 5x increase, and that number increases. So in the US alone, we will invest $500 billion in infrastructure for transmission to meet those decarbonization goals. And this is really our vision. So on the far panel, you'll see a 345 kV line with 12 MVA of power. And then on the near side panel, in the background, you'll see the VEIR lines that have been reconductored using a lower voltage, so 138 kilovolts, and transmitting the same amount of power through that existing right-of-way. And that's really the really important lever that we're trying to play, is to re-permit or add new rights of way. You have to go through public review and process. To get more power through those rights of way, you need to increase the voltage, which requires wider rights of way, higher towers. With our technology leveraging high temperature superconductors with zero resistive losses, we can put 5 times as much power through an existing right of way. And so what we really talk about here is we make high voltage transmission or bulk power transmission look like distribution. So those would be the 35-foot wooden poles that you would see out in the street in front of your house. Again, kind of taking it from the graphic to an area that's required for this right-of-way, this slide shows on the far panel what you would need in towers and rights-of-way for 5,000 megawatts of power. The lower portion is a reconductoring, or looking at using a high voltage, high temperature superconductor for that same amount of power. And as you can see, the area is significantly less. On the near side panel that we talk about here would be a reconductoring project. So think about, again, constrained right-of-ways. A utility wants to put more power, getting the renewables to where they need to be, but they just cannot expand the right-of-way. There's no way that they're going to get through that re-permitting process. Not in my backyard is the common term. And what we're looking at here is using a conventional 115 kV line, AC line, and this is predominant across the US as sort of a 40-year-old voltage class. But as we look at infrastructure in the US, 60% of the circuits that are built in the US today are 60 years old plus. So this voltage class exists. A utility wants to increase the amount of power they can get through that area. If they use a conventional conductor, they can max out at about 180 megawatts of power. Reconductoring that with our high voltage superconducting cables, you can get 1,000 megawatts. So again, simple numbers are 5x the amount of power with the same voltage class. Some of our milestones and stages of what we're looking at. We're now in our A series. We're doing, at the end of this year, we'll deploy an overhead cryogenic demonstration of the technology, and then move on to high voltage, high power in the following financing round. Partnership asks, I mean, we're really looking for equipment vendors, so really around substation equipment, transmission users, so utilities and alike, and then other entities, regulatory and legislative groups that we're looking at as we develop the technology. Thank you.